So we will look at Bessel functions and two of its applications. So one is a communication application, frequency modulation. The other one is on the classic application on a spring model. Except I'm going to do two qualifiers. A damped spring, which is also reasonably well known, but an aged, in other words, how does the aging come into it? And that involves, interestingly, the Bessel functions. So rather than introduce the Bessel functions, it's just to start with the FM transmission. And so there you have a carrier, and then the phase part is where the message is. So this could be frequency modulation or phase modulation, depending on whether the message is directly proportional to the phase or proportional to the instantaneous frequency. In any case, to get a idea about the bandwidth, etc., it's consider one single component as the message, FT. So this is phase modulation or generally frequency modulation. So the question is, if you take this, this looks like omega naught t plus beta sine b naught t. So b naught is the single component, and question is, if I call this to be E of t, the transmit signal, what is its bandwidth? How do you decompose this, etc.? So the easiest way is write this as the real part of complex part, omega naught t plus beta sine b naught t. And this, of course, we can write it as real part of e raised to j omega naught t e to the power j beta sine b naught t. So all the difficulty is here, so we'll call this g of t. So first thing we notice is g of t is a periodic function with period 2 pi over b. So that is a Fourier series expansion. So gt is a periodic function with period 2 pi over b naught. Because you simply substitute into this, you get back the same function. So this is a Fourier series expansion e raised to jk. Omega naught is b naught. This is omega naught. No, I meant that is t. And so this gives us b naught is omega naught, which is 2 pi over t. This is omega naught. 2 pi over t is omega naught. So that happens to be b naught. So this expression, k from minus infinity to plus infinity, and the ck is 1 over the period minus t by 2 to t by 2 gt e raised to minus jk b naught t dt. So let me substitute for gt. So that's 1 over t. T is 2 pi over b naught. So minus b naught over pi. T is 2 pi over b naught. So this is minus pi over b naught to plus pi over b naught. Gt is e to the power j beta sine b naught t, then this term minus k b naught t dt. So here we can make a simplification or a change of variable. Define x to be b naught t. So dt is dx over b naught. And so this b naught and this b naught cancels. And when t is minus pi over b naught, x is minus pi. So this goes minus pi to pi, 1 over 2 pi e raised to j beta sine x minus kx dx. So notice this is an even and odd part. This is a symmetric region. So you have this function is odd in x because this is odd, sine x is odd. So you have cosine of an odd function, then sine of an odd function. Sine of an odd function is odd and that goes away. So this only has this component. And this is what we will define it as the jth Bessel component, jk of beta. So beta is here, k is here. And consequently, this gt can be written as summation jk beta so it will be here. This will become summation jk beta e to the power jk b naught t. jk's are real. Notice that it is cosine here, so this is real. And if you combine the two exponents and take the real part, this will turn out to be k equal to minus infinity to plus infinity jk of beta cos omega naught plus kb naught t. So this is a standard expression, nothing new here. So if you look at the spectrum as opposed to this, wherever omega naught is, you have a carrier, then you have all the other terms. So the bandwidth explodes, right, on this, symmetrically on this side also. So this will be the power spectrum from here, because you have omega, k equal to 0, you have omega naught, the carrier, with the j naught of beta. And at some omega, k omega naught, you have jk of beta. So the jk's are well known. They are plotted essentially, they go like this. This is j naught of beta, and all the other j terms come from and these are the zero crossings. They have several properties and so on. So this is quickly the FM application, but I want to get the motivation from here and discuss a couple of other problems, which has nothing to do with FM. So what I am interested is this, the term for jk. So I am going to copy that and we'll go from there. So basically for FM, even if you want to transmit a single frequency, by the time, the moral of the story is by the time you transmit, it occupies a large bandwidth. If you use Carson's rule, this bandwidth is roughly beta plus 1 multiplied by b naught, two-sided bandwidth, multiplied by 2. And so you need a premium bandwidth. That's the FM. So what interests me is the jk term, and show some other applications where this jk comes up. So jk beta is 1 over 2 pi minus pi to pi cos beta sine x minus. So I'm going to write it as beta j of nx. And this is my starting point, and all I wanted to show that this comes up. So this expression I copied from here. This is jk of beta. And generally the pictures are like this. So I'm going to dive into these Bessel functions a bit more. Since it is real, I can write this as 1 over 2 pi minus pi to pi, as we had before, e raised to j instead of cosine beta sine x, and e raised to minus j n x. So this I'm going to expand this using the e to the power terms. So this is going to be, so if I e raised to j beta sine x is summation j beta sine x to the power k over k factorial. K goes from 0 through infinity. And so that becomes so this sine x, I'm going to write it as e raised to jx minus e raised to minus jx over 2j. So this j would cancel with this, and you would get a beta by 2 coming from here to the power k, then 1 over k factorial, and we have e raised to jx minus e raised to minus j x to the power k. And so here k goes from 0 through infinity, and this I'm going to expand as a binomial. Or before I do that, if I substitute here, this becomes summation k equal to 0 through infinity beta by 2 to the power k 1 over k factorial, then the integral 1 over 2 pi e raised to jx, or e raised to j theta minus e raised to minus theta. We can replace the variable by theta, and to the power k, then e raised to, then there is a e raised to minus jn theta d theta. For this integral I change x to theta. It's a local variable anyway. Now this factor, this integral, you can quickly see that it is 0 if k is less than n. And that logic is, if you can expand this as another I equal to 0 through k choose I, e to the power I, e to the power k minus I. So this would be e raised to minus j k minus 2i, right? Because e raised to ji with a plus sign, e raised to jk minus I. So theta. Notice that this goes from 0 to k. There will be always one term. So if this only goes from 0 to k to minus k, because with the 2i goes from 0 through k. So when I is 0, it is k, and the other extremity is minus k. But in any case, so if the k is less than n, this will dominate. This multiplied by this integrated over minus pi to pi would be, so this multiplied by e raised to minus j n theta. When you integrate this, it will be 0 if k is less than n, because then this will dominate. So the only case where it will be non-zero is when k is greater than n. And consequently, we can rewrite, we will take the summation for k greater than n. So Jn of beta goes from k equal to k greater than n. So I am going to a non-zero. So I'm going to put k equal to, rather than say k equal to, going from q equal to 0 to infinity. K is n plus q. So just tagging along all the terms. So it is beta by 2 to the power k. K is n plus q. Then 1 over n plus q factorial. Then 1 over 2 pi minus pi to pi e raised to j theta minus e raised to minus j theta to the power k. K is n plus q and e raised to minus j n theta d theta. This needs to be simplified. So if I pull out e raised to j theta outside, it will become e raised to j theta multiplied by n plus q. N would cancel. So this expression would become just this expression, minus pi to pi, 1 over 2 pi, 1 minus e raised to minus j 2 theta to the power n plus q e to the power j q theta d theta. And to simplify this, we just expand this. So this is I equal to 0 through n plus q minus 1 to the power I summation e raised to, so first term raised to the power I. So minus 2i theta and e raised to j q theta minus pi to pi. And there is an n choose k, n plus q choose I here. So if q is odd, this will be, this plus this will be always, this will be 0 because this will never go to 1. And so this integral is again 0 if q is odd. That means q must be 2m even. So in that case, Jn, so I'm going to put q equal to 2m and redo this. So this will become summation m equal to 0 through infinity beta over 2 n plus 2m 1 over n plus 2m star 1 over 2 pi minus pi to pi 1 minus e raised to minus j2 theta to the power n plus 2m, and e raised to j2m, because q is 2m theta d theta. This needs to be computed. And this, if you expand, this is summation I equal to 0 through n plus 2m minus 1 to the power n plus 2m, I mean minus 1 to the power I, n plus 2m, choose I, e to the power minus j2i theta, then e raised to j2m theta d theta. And there is integral here, minus pi to pi 1 over 2 pi. You can see this integral will only have value when m hits I, and all other values, when I equal to m, all other values will be 1. So this will be 1 when the variable I is m. That's the only contribution. So we'll put I equal to m. So this will read now m equal to 0 through infinity beta by 2 to the power n plus 2m 1 over n plus 2m factorial, and when n is I is m, this is minus 1 to the power m, then n plus 2m, choose m. So this is n plus 2m factorial, then n plus m factorial, then m factorial, because n plus 2m, choose m. So n plus 2m cancels, and we get this expression. This is a standard expression. I was just deriving it. So that's some m equal to 0 through infinity minus 1 to the power m n plus m factorial x over beta over 2 to the power m from plus n, from here n plus 2m. So let me take the last expression, and so we have a so I'm going to change the variables a little bit because it's easier to write with so this is good. So I'm going to also write Jn of x. Instead of beta, I'm going to use x here. So this will be 1 over 2 pi minus pi to pi cos, this is x. So I'll use some other variable here, sine theta minus n theta d theta. But what we have shown is this as an expression, the last expression. M equal to 0 through infinity minus 1 to the power m n plus m factorial x to the power 2m, then there is a 2 term, and x 2 to the power 2m plus n. So several ways it is written, in which case I should also, so you can add an n here, or you also write it here. So this is the power series expansion for Jn of x. As I said, the quality, so you can see when n is 0, it starts with 1. All other, when n is all other integers, the value at origin is 0. So the Bessel functions, so oscillations you can see from here, everything else will start. This is some jkx, and this is j0. So you can see that if you put x equal to minus x, you can see it's because if x equal to minus x, this will be minus x to the power 2m, so this remains unchanged. X goes to minus x, you get a minus 1. So you also very clearly see that Jn of minus x is minus 1 to the power n. Jn of x. So that's easy to see from this power series expansion. You can see from here also, but it's a little more work. And similarly, j minus n of x also is minus 1 to the power n Jn of x. To see that, possibly it's better to use this expression. If you put minus n, this will become plus. So define a new variable instead of x here, pi minus y, and rearrange, you will get this expression. So if once we have this power series, so we have two expressions. We have this expression, which I rewrote in terms of x here, and for this there is a power series here. So from this power series I'm going to develop again a classical result, a differential equation which the Bessel function satisfies. It's a second order differential equation. And for that, we'll take the derivative of the Jn with respect to x, of course. So we'll use this expression. So I'll copy it here. Jn of x is minus 1 to the power m summation m equal to 0 through infinity. Since I want to take the derivative, I am going to put all the x's together. So this is n plus 2m, and here 2 to the power n plus 2m, n plus m factorial, m factorial. This is what we start with. And the derivative Jn of x with respect to x gives us n plus 2m x to the power n plus 2m minus 1 over n plus m factorial, m factorial. If I take the derivative one more time, this becomes minus 1 to the power m, n plus 2m multiplied by n plus 2m minus 1, x to the power n plus 2m minus 2 divided by Okay, so now I am going to multiply the last expression with, rather than rewrite again, I'm just going to multiply this with x squared. So that only thing is this power would go away. And here I'm going to multiply by x so that all the powers become equal on all the three. And now if I add these two, let's say 3 and 4, so you get x squared double derivative of j n of x plus x derivative of j n of x. So we can do it by looking at it. Notice that n plus 2m is common, n plus 2m is common. So you have n plus 2m minus 1 plus 1. So when you add this plus this, think of 1 here. So this will become n plus 2m squared. So So this will become a summation minus 1 to the power m, n plus 2m squared. Rest is the same, x to the power n plus 2m divided by 2 to the power n plus 2m, n plus m factorial, m factorial. Now if you expand this, of course you get n squared plus 4m squared plus 4mn. So that's 4m multiplied by n plus m. N squared is a constant. So you can see that this will become n squared, then you have minus 1 to the power m, x to the power n plus 2m over 2 to the power n plus 2m. So this is nothing but j n of x. Plus you have 4m here. So m will cancel with this, become m minus 1 factorial. So summation m equal to, so first of all, since there is an m here, when m equal to 0, the whole thing will go away. So this summation starts from 1 through infinity first. Then we can cancel the m. And the 4 will make it, here 2 squared will go away. So this will become n plus 2 multiplied by m minus 1. And n plus sum cancels with one term here. So this becomes n plus m minus 1 factorial, m factorial. And the numerator you still have minus 1 to the power m, all the x terms, x plus 2m. So if you pull out one outside there also, then there is an extra 2 there. So notice this last term, it's easy to see, right? If you define m minus 1 to be a new variable I, then this is easy to see, this is minus x squared j n of x. Big, right, so you get the identity x squared d squared j n x dx squared plus x dj n x by dx plus So this is equal to, not plus, this is equal to remove these two is equal to minus x squared and then plus n squared. Both are j. So this is n squared minus x squared j. So this is written in this form, x squared d squared jn. So whenever we see a differential equation of this form, then it is its a solution is Bessel function of order n. So I have derived this also. Let me copy this and get rid of all the. So this is the differential equation satisfying Jn of x. So if this is Jn of x, all this was calculation. Notice that here when you put m minus 1 equal to I, this will become 2i, and I'm going to pull the x squared outside. This will become I equal to 0 through infinity. This will become I plus 1. So this will become minus, and this will be I, and this will be I. And this was already m minus 1 factorial, so that will become I factorial. So that will be Jn of x. Anyway, these are standard expressions, nothing new. I just derived it from basic principles. And I'm just going to clear up the road by copying the differential equation. So the differential equation is x squared jn y dx squared plus x dy by dx plus x squared minus n squared y. Of course, y is 0. Then yx, one solution is, let's just worry about one. There are two independent solutions. Now it's also easy to see that j minus nx is also a solution because this is n squared. In particular, if you put n equal to 0, x squared, that's the solution for the 0th order Bessel function. So that is j0 double derivative plus x j naught of x derivative plus n equal to 0, so x squared j naught of x. So is the solution to j naught. You know, I want to discuss two applications based on, actually one application, but 2-3 different cases. But before I do that, there's also an interesting result for. So in a problem, if you can bring the a problem to either one of these differential equations, then the solution will involve Jnx. So several physical problems reduced to this vibrations of a membrane. But in particular, I want to look at an ideal spring and also a damped spring. So for an ideal string, F is minus kx. In other words, the force which is m multiplied by the acceleration is minus kx. So we can write this as d squared x by dt squared plus k over m. So k over m is a positive quantity. So if you write this as omega 0 squared, x equal to 0, and that leads to the standard solutions as cos omega naught t and sin omega naught. So the spring oscillations. Now, if you bring in a damping coefficient, in other words, so that is some friction or whatever, but proportional to velocity, in other words, in addition to, so here the force is, as you stretch the string, the tension is proportional to the whatever amount you are stretching with that. So that's the basic equation that gives to this ideal oscillations. Now, if you assume here that it's also there is a drag or whatever depending on the velocity, then this equation rewrites to d squared xt by dt squared plus c over m dxt by dt and plus k over m xt equal to 0. So this is a quadratic equation, and if I call this as before omega naught squared and this as beta, we'll rewrite it as d squared xt over dt squared plus beta, the derivative. Again, it's a standard equation, differential equation, and its solution is, there are three cases. In other words, if you try a solution of the form e raised to, let's say, alpha t, if you substitute it here, you can see that alpha squared plus beta alpha plus omega 0 squared must be 0, plugging into this. So the roots are for alpha 1, 2 are minus beta. Remember, beta is positive if these quantities are, m is positive, plus minus square root of beta squared minus 4 omega 0 squared. So depending on whether beta squared minus 4 omega 0 squared, there are three cases: positive, 0, negative. So this will be the overdamped case, I guess. And this is critically damped. And this is underdamped. So let's call this quantity to be gamma squared. But even in any case, because it is, this will be in magnitude, gamma will be always less than beta, you can see here. So if beta is positive, then it will decay. So that will be the two components, and the general alpha 1 of course will be minus beta. So in the overdamped case, gamma is positive. So you have two solutions like this. Both are negative. So the solution x of t will be of this form: e raised to minus alpha 1 t plus b e raised to minus alpha 2 t. This is Euler's technique. So in this case, it is severe. It goes down real fast, right? Because both alpha 1 and alpha 2 are negative. So that's the case 1. In the case 2, critically damped, this quantity is 0, gamma is 0. So the two solutions are, you have one solution which is x1t will be of the form a e raised to minus beta by 2, right? The solution of this is this divided by 2. So this is minus beta by 2, and you need a second solution. So that will be, again, I'm not going into the details, x2 of t will be by D'Alembert's principle or whatever, you can, the t e raised to minus beta t by 2. So again, they are decaying. The third case is this is negative, so you can write it as alpha 1 as minus beta 1 plus j omega naught by 2, alpha 2 as minus beta minus j. So if you combine these two together, you will get exponentially decaying oscillatory terms, because the minus beta will take care of the the solutions with the third case will be like this. All this is still ideal, or this is not ideal, this is the ideal spring. Motion, the damping, without damping it oscillates forever. With the damping or some resistance, the oscillations die out. And it's interesting, a slight extension is where this coefficient decays with respect to time. So that's the application I want to look at. So that's what I mean by aged spring. So by aged I mean the K decays something like this is over time. K instead of the constant maybe slowly decays with respect to time, so that the differential equation becomes now so previously we had here just a constant K over M. So I'm going to modify this as with a decay. So this is a new equation that need to be solved. So this was a breeze. There was nothing to solve here. Standard equations. So to define this, we are going to define a new variable. To do this, new variable. You will see why all this crazy planning. So this is the new variable we are going. Instead of t, I'm going to define this new variable. Then notice that du by dt is simply minus a by 2u. So the damped equation was damped spring, which also I want to reconsider. The differential equation was d squared xt by dt squared plus beta dxt by dt plus omega 0 squared xt. And after doing this, I'm going to rewrite the solution in terms of u. So xt will be written in terms of yu. So question is, what is y? So xt is yu. So we want dxt by dt and its derivative. So that's dyu by du and du by dt. For du by dt we have minus a by 2. So that's minus a by 2 u dy u by du. Now we take the second derivative. So that is d squared xt by dt squared. So that's d by du of dyu by du and du by dt. So that's minus a by 2, this one, and derivative of this, so that's going to be minus a by 2 du by du, which is 1, then you have dy by u by du, then minus a by 2 u d squared by u by d by u squared. Okay, so if you plug this into this equation, so 1 becomes, remember d squared xt by d, so that's a squared by 4 common, and then you have so something is not right here, so a by, oh, so that's good. Oh, multiplied by du by dt, I didn't copy this well. My du by dt is minus a by 2 there is a u here, that's what I was looking. So this itself, if you simplify, this becomes a squared by 4, then u squared d squared y by du squared plus u squared here, u dy by du. All right, let me plug it here. So this becomes u squared d squared y by du squared plus u dy by du, and so that's the second derivative here, going back to this expression. Then this quantity is, now you can see this whole quantity is, if this is u squared. U squared multiplied by, so this is not u squared really, u squared is, u squared would be 4 over a squared, so this will be a squared over 4 multiplied by u squared, k over n. So this is plus a squared over 4 u squared y equal to 0. So if you look at this a squared, so this must be true, u squared d squared yu by du squared plus u dyu by du plus u squared dyu must go to 0. But if you compare this expression with this, it's exactly the same. So we conclude that yu is j naught of u, and this j naught is, at least one solution is this, u is 2 over a square root of k over, which is omega naught e raised to minus at by 2. So this is the, if the coefficient of damping begins to age with respect to time, the behavior is no nice sine and cosine, but it is j naught. But j naught itself, I didn't show you the proof, can be approximated as, I think, square root of 2 over pi x sine x, I think. So it's sine but with an exponential. So this is one this is the aging on the ideal spring. So I want to conclude this with considering one more term. So I want to consider the same aging but on a damped spring. So here the equation is d squared xt by dt squared plus beta dxt by dt plus omega 0 squared. So here I'm going to assume this e raised to minus at. This is the effect of age, x of t. So we want to solve this. So notice this, this is where the damping comes in. Now, so again, since this worked so far, we'll use the same u equal to 2 over a. This is omega 0, e raised to minus at by 2 as the new variable. So we have all the quantities worked out, we just have to plug it in here. So for this equation now goes to a squared by 4 u squared d squared y by du squared plus u dy by du plus beta and dxt by dt, that's here. So for the first line, minus a by 2u dy by du. So aged ideal spring, the solution is, I want to use that space, x of t is constant but j naught of 2 over a, so other constants, omega 0 e raised to minus at by 2. This is also oscillates, but faster than sine, etc. So we use the derivative. Then the last term is omega 0 squared. So this is going to be as before from here, omega 0 squared, this quantity is a squared by 4 u squared y of t, y of u equal to 0. So if you simplify this, getting rid of the a squared by 4, or at least this will read now u squared d squared yu by du squared. Notice dy, there is two terms. There is an a by 2 here. So if you put one more, this will become 2 beta over a. So you have one term here. So notice that this equation is very close to this, but not really, because here you have this term sitting here. So interestingly, somebody has shown that if I call this, if you define P to be 2 beta over A, this quantity, in other words, if you write this as, P as beta over A, so that this equation now reads 2p. We can write it like this. If you define p to be beta over a, it's a positive, so p is a positive number. Then with one more transformation, I don't know who has shown this, but the result is so instead of yu is what we are looking for. If I define this to be u to the power p z of u, so we just need to figure out what this is. u is 2 over a. So notice that dyu by du would be p equal to pu to the power p minus 1 zu plus u to the power p dc by du. And you need the second derivative also. So the second derivative of y with respect to u is p multiplied by p minus 1 u to the power p minus 2 z plus the derivative p u to the p, the derivative of this, and which will be the same as this. So this will be plus 2 times p up minus 1 derivative of z with respect to u plus up second derivative of z with respect to u squared. If you substitute and this and this into this and simplify, I'm just going to write the final result. You will get so it's just calculations. You just need to substitute those two, and so you'll get u squared z squared zu by du squared plus u dzu plus u squared minus p squared multiplied by zu equal to 0. So you get this expression, but you notice this is the same as this. So we get z of u is actually jp of u. So bottom line is here, x of t is u to the power p jp of u. U is of course that whole quantity, some constant e raised to minus at by 2. So u is some constant to the power p e raised to minus ap t by 2, then jp of constant e raised to minus at by 2. So it's doubly exponential. This is decaying by its own terms. So it's a complicated problem. A spring is not only damped, it's also aging with respect to time. So the interesting thing is this, even though I keep talking about spring, a lot of other problems, for example, an aging RLC circuit exactly has the same solution. As the components age, the oscillations, the damped oscillations become even worse. So maybe even population models, etc. The decay, what happens in the long run with respect to time. So basically some constant, then exponential term. This is again, A is for the age, P is the Bessel function order, the exponential decay with respect to time, plus it involves multiplied by so it's essentially something like this. So this is very interesting to see the plot of this without or with just decay, and also compared with respect to where we started with, which is the ideal spring.